Just checking, was everybody able to download and install the packages?
Hi everyone, welcome to the tutorial today on Introduction to Spatial Data Analysis in R. Please type a yes if some of you type yes that you are able to see the screen, my title slide. That will be great. And if you're able to hear me all right. Okay, great. Thanks, Aditi. And some of you are installing packages. That's okay. That's okay. You can do that while the tutorial is going on. We will do exercises in the last half an hour, which is 1.5 hours from now, I think. It's a 2 hours tutorial, and the last part of the tutorial we will spend on exercises. So it's okay. You can take the time till then. We will also have a 5 minutes break in between, so that will be some time to do it. And please continue to post your questions in the chat or in the Google Doc like Aditi mentioned. So today's my co-instructors are Aditi Upadhyay and Pratyush Agrawal. I'm Meenakshi Kushwaha, and it's such a pleasure to be sharing this information and sharing this knowledge with you. I hope that it is, if you're new to spatial data in R, you have, this is a good use of your time and you learned something useful today. So with that, I will get started. So I'll skip this. This is the logistics stuff that Aditi already mentioned. So the first thing today, we will start with a very, very brief intro to map projections. And hopefully it is just enough to help you get comfortable with the basic concepts of theory behind the spatial analysis in R, theory that you need to be able to get started with spatial analysis. So first off, map projections are two-dimensional representation of a three-dimensional Earth. And how is the two-dimensional representation done? Here, this illustration shows there are different ways. So for example, by two-dimensional, I mean a sheet of paper, your two-dimensional, your flat screen, something flat. So representing the spherical Earth on a flat surface. And so imagine holding a paper, like a huge, huge paper on the North Pole, and then projecting each and every location on the Earth's surface onto the paper. And this is what the bottom figure, this is what that would look like. Now, you can also do a projection using a conical surface, and that would look different. A cylindrical projection where where there is a flat surface surrounding Earth, and then projecting on that surface, that will look something like this. So depending on how Earth surface is projected, the final map will be different. And this process is called projection. One concept to get really familiar with when you're working with spatial data is coordinate reference systems, or CRS. CRS, the short form we will use a lot. CRS tells us how a map is related to real locations on Earth. So for example, maybe you have a map where the location is marked by numbers 130, 12. These numbers by themselves are not meaningful if we don't know where the origin is and what the units are. And that is what a CRS tells us. Broadly, there are two categories of CRS: geographic coordinate system, GCS, which is, as you can see, it is unprojected, it is circular, so it is on the Earth's surface, and projected coordinated system, which is what we saw in the earlier slide. It's Earth's drawing on a 2D flat surface like on a paper map or a computer screen. A GCS is round, and so it records locations in angular units like degrees and directions like west and north. And projected coordinate systems are flat, so they record locations in linear units, usually meters or kilometers. Now, when you have your spatial data in R in context of the CRS, these are some of the first questions to ask. First, we need to know if the data is projected. If the data is projected, which projection system is used, or which CRS, which coordinate reference system is used for the data? And that usually you'll find from the source, wherever you download the data from, if from a Met agency, anywhere. So the source should be able to tell you what the CRS is for the data. If the data is not projected, then you need to project it before mapping and use the correct system. So there's a lot of theory that goes behind what correct system that you have to use. And usually if you're working with the data for a while, you would know it. And the decisions are based on theory and how to what is most appropriate for the parameter that you're analyzing and for the region that you're analyzing the data. Most common projection that you'll see a lot is WGS84, which is good for mapping global data. So Google Earth also uses the same CRS system. When something to be careful about, when you have data or we often combine different layers together. If they're in different CRS, they need to be transformed to the same CRS so that they align with one another. This is very similar to, for example, if you're measuring, if you're working with lengths, everything needs to be in meters or kilometers. So your units should be same for with volume, kilogram or milligram. So it's like having the same units when you're doing mathematical operations. With spatial operations, you need to have the same CRS to be able to combine things together. Now, one question may be why beyond the GCS and projected coordinate systems, why do we have so many CRSs that we need to choose from? One of the reasons is that there are many different models of Earth. And so there are different algorithms for projection. And so different coordinate reference systems. The choice of which projection is used to map is based on minimum distortion and for region, and it depends on the region of your interest and your parameter. There are three components of a CRS: a projection that we talked about earlier, an ellipsoid. So remember I talked about the different models of the Earth. So ellipsoid is a technical term that defines the general shape of the Earth. Imagine an ellipse and then imagine it in a 3D, just like a circle, and a 3D of a circle is a sphere, something like that. Very, very rough definitions. So ellipsoid defines the general shape of the Earth. For example, in the figure here, imagine that this red line here, it depicts the Earth in 2D. It's an approximation of the Earth. This is the mean sea level. So this is like the Earth's surface. And this is our ellipsoid. So this is the mathematical model of an ellipsoid that is best fit for the Earth as a whole. So this will lead to one CRS. Now, this is good for a global data set, but what if I wanted to analyze data at the South Pole? And here you can see there's a gap, there's a big gap between this. They don't align well, this ellipsoid and the Earth's surface. So I might choose a different type of ellipsoid or a different model that aligns, that works better for this region. And that would lead to a different CRS. Then the third component of a CRS is a datum, which defines the origin. Now, this is a lot of detail, lot of theory before we get started with the packages, but On day-to-day basis, you won't need all of these theories and all of these details, but this is just so when you are looking at CRS, some of these terms are familiar and you know what those terms mean. So that sums up the theory part of this session. And with this knowledge, we hope that you'll have a good sense of handling the projections of your data. Next, a quick introduction to the types of spatial data. There are two types. One is a vector data, which has geometries like points, lines, and polygons. Point data, just what it sounds like. It's location points on your map. So point data could be tree data, location of trees, location of airports, every point denoting the location of an airport, every point denoting maybe a pollution event like a chemical spill, which could be an area, but the point is denoting the center of that event or the cities in a large map. Lines, another geometry is lines. Again, it could be a phone line, it could be roads or highways, rivers. So think of, yeah, just line is a different geometry in vector data. And then areas. Areas are points, areas or polygons that are points connected together. They could be a range of animal movement, watershed area, administrative area, which is probably most familiar, like a city boundary, state boundary, country boundary, things like that. So these points, line, polygons, they comprise vector data. Now, vector data is stored in a very different kind of data structure. When I say by different, I mean if you've worked with CSVs or if you've worked with Excel files, the data is in a table format, which is in a single file. Here, shape files data is stored in something called shape files. And shape files are not just a single file, they are a set of files. So that's the most important thing to remember from this slide, that shape, when you think shape files, you're thinking multiple files. And the data is distributed between over multiple files that store information about location, shape, and attributes of your features. By attribute, I mean any other characteristic which is attached with your geometry. For example, if you're dealing with road data, you may have information on road length. You may have information on road type, whether it's a highway, small street, arterial road. So all of that information, apart from location, apart from the coordinates, all of that information attached to your feature, attached to your geometry, they are called attributes. So shape files store data, store information about your location, shape, and attributes. And like I said, there will be multiple files. And so your shape files will have at least these three files with the extension shape, SHX, DBF. And they may also have these extensions, but they are not optional. Sorry, they are optional, they are not essential. And all of this information is, this is like, take it to heart when you're dealing with shape files. Remember this, that they are multiple files. Otherwise, this can happen, which I have done a lot as a beginner, where I would attach just the shape file extension, just one file in the attachment, or give that if someone has asked for a shape file. Or even from my folders, I've deleted other files because I didn't know that the rest of the files are actually also shape files, and they all are needed to be able to work with that vector data. So that's the reminder. Next is raster data. Raster data is the second type of spatial data. It doesn't have geometries like the points, lines, polygons that we talked about. This data is in form of grids, so it's gridded data saved in pixels. And if pixels, you're thinking images, that would be correct. So images are raster data. And the file extensions along the same lines are what would be your file extensions for images like JPEG, TIFF, or PNG, anything that has pixels. here is an example. This is an aerial shot. And if we zoom in, we can see each pixel. These little squares are each pixel, and every pixel is around is exactly 1 square meters, and each pixel has a value, which probably maybe for this image, it's showing the level of vegetation. So that's the raster data. And now let's do a quick quiz, just to do a knowledge check. Yeah. A new poll has been launched. Can you see it?
Yes, we can.
Answer. Okay, I see a lot of correct answers coming in. We'll take a minute. Okay, I will close the poll now. And okay, so the question was, which of this is not a shapefile? And the answer is plant CSV. Many of you answered. We received all correct answers, whoever was able to vote. So great, thank you. And let's do the next poll now. Okay, a lot more people were able to poll this time, and we've received all the correct answers. So yes, I'll end the poll now, and sharing my screen again. So the correct answer is plants.xlsx is not a raster file, it's an Excel file. All the other file formats are raster files. So quick recap of this section. We learned about map projections, coordinate reference systems, and some questions to ask with you when you first see your data. Types of spatial data, vector data, and raster data. Vector is the one with geometries, points, lines, and polygons, and raster is your grid data. So that's the summary of all the theory background that you need for this session, we hope. And I will, before passing on to Aditi, any questions right now that we can quickly answer?
We don't have any questions right now.
Okay, thank you, Pratyush. So with that, I'll pass on to Aditi, and Aditi will talk about the packages and walk you through some demo and exercises. Thank you.
Hi, thank you, Meenakshi. That was great. Let me share. Okay. Can I request you to stop sharing? Yes, perfect. Thank you. Okay, so yeah, so the heroes of today's exercise and the whole workshop are these packages: SF, raster, and stars. Uh, these fuzzy monster. This I think most of us are familiar with these fuzzy monsters. It's directly taken from Dr. Alison Horst's tutorials for SF package. We'll talk about the SF package for some time. So SF package is a simple features package which uses all these different functions with a prefix of st underscore, just like PostGIS. And it can be used for reading, writing, manipulating different spatial objects which have attributes and geometries. So attributes can be treated as different columns, and geometries are something we'll discuss. I'll just recap a little bit of how it is used in SF package. So the different types of geometry which is used and which can be identified in the SF package are point, which is a single point, multi-point, which are multiple points, line string, which is two or more points connected by a straight line, multi-line string, set of multiple lines, and then a polygon, which is a closed circle or a zero or a closed ring or a closed object, or multi-polygon, multiple polygons, or you can also have a geometric collection of any of the combinations above. Like you can have a point, you can have a line, you can have multi-point, etc. So all these geometry types are identified by SF. So why do we use SF? There are many packages, spatial packages, which are available in R. Why only SF? So the main advantage of SF and why people are using it widely is because it treats your spatial data, the complex spatial data that is in our mind, in a very simple data frame format. And it can be used with a pipe operator. Hence, it can be used with tidyverse very easily. And the backend, the actual whatever calculation is going on behind, it needs a different support, like proj libraries, geos library, jidal library, which are written in C. So those can be is directly linked to SF for making all our geographic calculations easy, and also handling the coordinate reference system. So it calls all these C libraries from the backend and makes our life easy by showing us only the neat things. So that is why we'll be using SF today. So I'll be doing demo and also talking about different functions, so I'll just load the libraries. I'll also be doing a demo. These are the libraries that we're using today. SF is the package which we'll be mostly using for vector data. That is, and then raster we'll be using for the raster dataset. Tidyverse because we want to use the pipe operator. Stars package, we'll use it only only in the end for two simple tasks, and leaflet for interactive mapping, ggplot2 for plotting, and ggspatial for annotation and all. Okay, so the sidekicks for today's workshop are the two data sets that we have. One, vector data is collected is a random data, a dummy data set that we created, which shows the presence of urban lizards in Bangalore, India. for for this year. It's a dummy data set, and the raster data is temperature data, reanalysis data, which we downloaded from Google Earth Engine for the month of March. Again, for this same spatial extent of Bangalore, India. Okay, now so we know the package SF, and we know how the functions in SF are there, st underscore, all the different functions that are there, area, distance, etc., which we'll talk about. So how do we actually read a particular CSV file and convert it into an SF object? So right now, does everybody have the data set? In the email it was shared, I think.
Yes, we have.
I'm sorry. You can also type in the chat if you have the data set, then I'll move ahead. Okay, somebody doesn't have the data set. I can actually share it now. Yes, it was shared as a .rar file. I can share the link of the. Pratyush, can I please request you to send the. Yes, thank you so much. So assuming some of us have already downloaded the packages, installed the packages, and downloaded the data set, I'm going to start the demo. Yes, this is just me loading the library. Sorry, I didn't do that before. So while that is happening, yes. So we have a data set called spotted.csv, which we'll be using for this tutorial, that is stored in the data folder of that RAR file. I'm just going to read this and call it data as simple as I would read a CSV. Let me check how it looks.
Aditi,
Yes.
we can't see the screen.
Oh, I am so sorry. I'm so sorry. Let me share my screen. Okay. Okay. So yes, I loaded the libraries and I've just run this command. And if you see here, let me run it again. And when I view the data, it looks something like this. So this file demo.rmd is also available in the same RAR folder. Please let me know if people have it. You can also share with other people if required. Yeah. Yes, now when I look at the data set, it shows me name. There are different rockogamas, geckos, lizards, etc. And there is latitude and longitude information. I now want to convert this CSV or a data frame into a proper SF object so that I can use SF package from now on to manipulate this data set. Again, I'm defining a projection string. So proj4 string is a particular kind of database where all these different projections is stored as a string. So you need not define your own projection system, do the math. It's all simple given as a string. You just have to convert it into a STCRS. Again, STCRS is ST underscore is a prefix. CRS is assigning a coordinate system. And I use this. This is my projection. This is the string I want, which is projection lat long, ellipsoid WGS84, and datum WGS84, the different parts of a of a coordinate system. This is the geographic coordinate system, which Google Earth also uses. Hence, all your latitude and longitude now you can assign a projection to it. That is the geographic coordinate system, and then look at the data. Right now, if you want to check the class of your data, it is a data frame. And I will, with another function, I'll be converting it into SF. So before that, I want to convert this simple string into a coordinate reference system in SF. And for that, I use a command called st underscore CRS, and I share the string here. I add the string here. And let me see how my projection looks like. And it has all these extra information that we didn't know, well-known text, as you don't need to look into the math here, as long as you know what projection system you will be using. Since it is just latitude and longitude, I am using the geographic coordinate system, the simple one. Okay, now moving on. There is, if you want to create any from a foreign object to an SF object, the command for it is st underscore as SF. Convert a foreign object to an SF object. You should add the data set. Then you specify the COORDS, that is the coordinates. The function has to know which is the longitude column, which is the latitude column. So the order is super important. Please remember, longitude first, latitude next. And also the column names have to match exactly, latitude and longitude. So it was capital L, hence this capital here. And then finally mention the coordinate reference system at which you want your data. So since we collected the data using Google Earth, we are going to use the WGS84 geographic coordinate system. Now, when I convert this, and I want to check the class of the data set now. It was a data frame before. I saved it as data underscore SF. Right now, it is an SF. Okay. Now, if I want to plot it, let's see what happens when I do plot a SF object. Okay, so sorry if people are not able to see here, but I can see small pink different dots spread across my plots pane and different names available here. So so the plot has understood it's a spatial object, and hence it will be plotted with proper scale, etc. by default. Okay, anyone, any issues still here, or can we move ahead?
Aditi, is it okay if we wait for 1 minute and take one question?
Yes, definitely.
Okay. So we have a question from Dulsa. I'm really sorry if I pronounce your name incorrectly. Is there any advantage or disadvantage reason to use vector versus raster data?
No, it depends on the purpose that you're serving. Like, if you want to understand the range of an animal's movement, then I would say go for a raster data set if you have supporting files. Like, I'm sorry, not exactly the right example. So if you want to if you want a smooth, continuous surface, continuous data set, then raster is a very good option, because raster is continuous, while vector is discrete. So you cannot have continuous data set of animal available or not available or not. But raster is something which is continuous, and hence you can get continuous data. So it purely depends on the purpose, but so you need to understand how to visualize the data set. Do you want continuous output in the end? Then you have to rely on taking raster till the end. But do you want vector in the end? Then you can keep using vector from the beginning. So did I answer your question? Okay. Yes, I hope everybody is able to catch up with it. Please let me know if it's too fast or slow. Yes, now I think we'll move on. So we were able to convert a CSV object which had latitude and longitude and a name to a SF object. Now your data is already converted from a simple data frame to a
Can you
spatial
share
object.
your screen again?
I am so sorry. Okay.
Thank you.
Yes, so I was mentioning that we converted a CSV to a spatial object already. So if you're wondering from where did I get these strings, this link is available here. It is available in the format of a string or also as a numeric code. So these help us to not do the calculation behind defining an ellipsoid, datum, etc. They make our life easier by giving us just a string and a code. So all these are available here if you want to check out. Now, I've understood that I've made a spatial object. Now I want to see it in a map. What do I do? So it is simple. Let's use ggplot. And okay, let's do it as a demo. Now I'm going to take ggplot. I'm going to plot this SF object. Since whenever we use ggplot, we define the geometry as a point, line, box plot, etc. Here we'll be defining the geom as SF and specifying the data as the SF object that we created. And then the final step is to add the, if you use ggplot, you would remember that you use scale x continuous, scale y continuous. So you need to provide a scale. And here it's the coordinate reference system. So that is the scale which measures. So I'm adding that everything default, a simple plot, how it will look on a map. So yes, so if you see in this plots pane, the points are randomly distributed, the location of these agama/lizards, and they are positioned correctly as northing and easting. So you just had to provide the data in SF as an SF object and specify geom SF and coord SF, the coordinate system. So it automatically understand that it's a geographic coordinate system and assigns these values. So hence we were able to plot. We'll make it more pretty in the end. Yes. So there are different small functions in SF which help us to make our spatial data more refine our spatial data and check if the data is correct or not. So one such function is st_is valid. So you can check whether the data or the spatial data has valid geometries throughout. Since we have 9 entries in this data set, you can just check this using the st is valid and specify the data set, and all the 9 entries have valid geometry. So if it was invalid, any one would be invalid. When I say invalid, it means latitude is out of range or longitude is out of range, such examples. You can always try it out and see if your data is geometry is valid or not. So I just wanted you all to take a quick look into data SF. If you see here, I am sorry I didn't show it before. We have lost the latitude, longitude columns separately. What has happened is a new column has been added, which is similar to a list column. It's not a simple numeric column. It's a list column which has like 2 entries, and then it is a geometry. So new column has been stuck to a previous data frame, and that's what SF does. It keeps all the attributes as it is, converts your spatial data into one column, and that column is always called geometry. Okay, so you can always check the geometry if it's true or not. And there are other read and write functions, which can write a simple features object into a database, and then also reading from a simple feature object using the command stwrite or stread. So again, here, though shapefile has many supportings, when reading or writing, you need not specify these files separately. Those automatically get created. So .prj file is for projection, .dbf file is the database file. So once you write it, it's automatically written. All the supporting files are written. Similarly, while reading, you need not read all the different supporting files, just SF is enough. And if you want to save the X and Y coordinates while writing the simple features object as a shapefile, you can use different layer options which are available, and you can definitely check them out. Yes. And other than just reading, writing from SF package, you can also create your own simple feature. So right now we are just trying to create one simple point, ST point, specify the longitude first, then the latitude. So the order is important, and then once you create it, you can check the class of P1. It is a geometry type is point, and the class is SFJ. Again, a geometry type of SF. So it has been converted from just a combination of points, numbers to a SF object. So how do we call these different geometry types? So again, add the prefix of st underscore and then add point, multi-point, line string, multi-string, polygon, or a collection. So if you want to have a collection of a point, multi-point, line string, etc., you can use the geometry collection. There are other two functions, very important function. So one is stcrs, if you want to retrieve or check the coordinate system of your data set. So st underscore crs, the lizard data that we have, and we get to know all the underlying coordinate reference system for this data set. And if you want to also check the geometry type, then you can use this function, which is stgeometry type, and then you can add the data here, your spatial data here. But remember, all these need to be in SF format. The class of the data should be SF, not just a data frame, because they all work with the geometry column. So they will go to the geometry, check it's valid, then calculate the CRS, etc., etc. Okay, now we, in the beginning, Meenakshi was speaking about coordinate reference system. So right now, what the data that we have is in geographic coordinate system, and we want to transform or convert this the coordinate system of this simple feature to projected coordinate system. So right now, I'm using a numeric code, not the string that I showed before. So it could be any way that you want to work with. The link is there in the slide as well. So I'm using Universal Transverse Mercator, the projection system, which is used for Bangalore in general. A lot of people use it. So I'm just going to take that for zone 43. So there are multiple zones. You can't define all India in one zone. So it's distributed with number. So it has a numeric code, and hence we'll transform our data set to that. Okay, now we know data SF looks like this. If you just check, and sorry if it's not visible, this is written 77.7 and 12.95, the geometry here. When I project it, let's see what happens. I am mentioning the projection system here. So this is the CRS equals. You can also add it just like this. So when this is done, let me view data SF. Yes. Now from 77, it has moved on to 79, 5, 4, 2, 7 point something, etc., etc. So what has happened is it has converted from the degree decimal to the meter, the projected coordinate system, where the units are meter. So this command is used for transforming it. Okay. Now we'll talk about geometric measurements. So whenever we work with spatial data, we have these basic, every time we need to do a few certain data analysis, like calculating distance, area, which everybody wants, all of us want to know. So again, the function names are very similar. If you want to compute Euclidean distance between different pair of geometries, then you can use st-distance function. So again, the coordinate reference system should be same. So right now I'm using the projected coordinate system because the unit is in meters. So when I calculate distance, the output will also be in meter. So I don't have to worry about that. Right now, I want to check, let me see how my data looks. I want to check if the rock gamma 1 and the rock gamma 2, which is number entry 1 and entry 5, how far are they from each other? So I'm going to use the function st-distance, and I'm going to specify first rock gamma, the first data set, and the second rock gamma, which is the fifth entry. And then I calculate the distance using the st-distance function, and the output is given to me in meters. So they are almost 17 kilometers apart. So that is one of the functions. You can also use area to calculate area. So there again, you need to remember that you need to have the coordinate reference system either in degree decimal or unprojected or projected in meters. Now we have a lot of geometric unary operations as well, using just the data set. So one of the important functions here is st buffer. So buffer is a determination of a zone around a geographic feature, which is within a certain distance of that feature. So what happens when we use st buffer? A new geometry is created. You need to specify what should be the distance or of the buffer of the zone. And it creates a new geometry altogether. Let's see how that looks. Okay, I'm going to use again the projected data set because I want to specify the distance in meters. So here I want to know if my data SF projected or all the lizards, the home range of these lizards, like how much range. I'm just assuming that they travel 3 kilometers in their lifetime. And if I use this function of buffer, let me see how buff looks like. Save it in BUF. Again, name is there, and now it has become a list column again with multiple entries at each point. And let me plot this. Okay, now those were the previous image was a series of points, and now suddenly it has become circles, big prominent circles. So these are the buffer regions of the range of each of the lizard. So yes. So there are other unary operations as well, like st-centroid, which gives the centroid of the geometry, or st-union, which can combine several feature geometries into one, or st-reverse, which reverses the node in a line. You can definitely try it out. Now next we go to geometric binary predicates, like intersect. So if we have to find out if two pairs of simple features geometry ever intersect, then we can use this command of st_intersects. You can specify the first simple feature object and the second feature. It will either return true or false. So right now I want to know if the first rock agama are they found exactly on the slender gecko? Do they intersect? So I'm just going to add that here, and it says empty. Now let's go and try it out. I'm going to see here. First, does the point intersect? It says empty. But what happens? I don't have any intersecting points. So what I'm doing is I'm checking if the same data set, do they intersect? What does it return? So it returns 1. That means true, that the two of the points intersect. So there are other geometric binary predicates which we can apply on pairs of simple feature geometry sets. They return true for matching indices. You can also, the others which are available are st disjoint if they don't spatially intersect, or a st within, which returns true if the first geometry is completely within the second geometry. And there are others as well. It depends on what kind of context or what do you want to achieve with a particular function. And there are other operations. So what are these other operations? So we do a lot of joining when it comes to data frames. So this kind of spatial join is also available. And that, yes, spatial join is also available, but that occurs based on looking at the spatial data or the geometries, not indices as such. Not the primary key here, if I could say, is the geometry of the both the features. Sorry. Yes. So right now, let's. There is another data set which is available, which was given in the data folder called spotted join. So we'll read it in the same way, but I'll name it as data join and read CSV. Yes, now let's see what this data join has. Okay, it has latitude, longitude, and length of each of the lizard or gecko. Now, okay, it is in latitude, longitude. Let me see the class right now. Class data join. Okay, it's a data frame. Now, if I want to convert it to an SF object, I know I have done this before. We have done this before. We had to specify the data, the CSV data that we have stored, and specify the longitude first and latitude later, and then define the projection, which is already defined here in the first string. And hence, when I do that, I convert my data join to data join SF. Now let me view data join SF. Sorry, pardon me. Yes, so right now we have the length and the geometry attached here. Okay. Now the predicate which I'll be using here is st join, but what should it join on? So I'm saying that the join should be based on st equals. So there are many predicates like this: st nearest, st equals, st equidistant, etc. So equals as in the latitude and longitude geometry should be exactly equal for this to join. So it works like a left join. So whatever is available here remains, and whatever matching feature is available in this will be added to the first data, a simple feature. So let's see how it looks. There were only 4 entries in data SF join and 9 entries here. So when we look at join, we get, okay, so name is present and all, and then length is available only for 4, where the geometries were matching or were equals. Hence, so we need to understand what is our what predicate do we need to perform the join operation. Now summarizing all that we have seen right now for vector data is SF package has most of the functions begin with st underscore. They can be easily used, and a lot of operations can be performed using this package, using read and write, using st read and st write, and also get information like coordinate reference system, the geometry type. You can also transform your data. A foreign object can be converted to SF, or you can transform the projection system of your spatial data. And certain geometrical operations can also be performed, like distance, area, buffer, intersects, unary, binary, both. And you can also work with multiple layers using stjoin and using a particular predicate. So that our spatial data set. Any questions still here? We'll be taking a break right after this for 5 minutes.
Hi, sorry, can I ask a question just by video versus typing it?
Yes, yes, definitely. Hi.
Hi, thanks so much. I'm totally new to spatial analysis, so I apologize if this is a really basic question. Basically, my question is like, what are the requirements of the object that you're converting from a foreign object to an SF object? Like in this case, we're using like the longitude latitude projection, but like, I think I just don't understand enough about like the theory. Like, could you convert from a different data type? Do you always have to have the columns longitude latitude? Does that make sense as
Yes.
a question?
Yeah, thank you so much. I think that's a very important question. Requirement is that it should have a latitude and longitude column if we have to convert it to an SF object, because the geometric column is created because you have these two columns. If you don't have latitude or longitude, then you might not, the package cannot convert it into a geometrical, and it should be numeric. So it should be the data type should be numeric, and it should have a latitude and longitude column. It can be in meters, like it can be 74,000 meters, which is a projected coordinate system, or it can be a normal, you can just pick up these and then create your data set. But the minimum requirement is latitude and longitude column.
Okay, thank you very much.
Yeah, thank you. Any more questions, or we'll take a break for 5 minutes? Sorry. Okay, we'll take a break then.
Meanwhile, those who haven't installed the packages yet, they can still do it, so that during the exercise, everyone has the packages.
Absolutely, and any questions also can be answered now. And all these folders, files, slides will be shared. So after the presentation, so you can do it anytime. Yeah, please let us know. Hi, if you're back, can you please type in the chat if everybody is back and we can start. Yes, okay. Most of us are back. Okay, now moving on to the, now we saw everything about vector files or discrete attributes file. Now let's move on to raster, which is more of a continuous data inflow. So raster data is something like an image, but that image also contains spatial information or the location information. So for all the raster operations from now on, we'll be using the package called raster. I am sure most of us were able to download and install the package. And if you want to read that particular raster, you just have to use the command raster, and the parameter that we pass is the location of the file, of the TIFF file. So usually for a raster image which has location information, we call it as a geotiff file, or here we are using the temperature data set of March 2022. And you can also create your own data set using the command raster, specifying the number of column and rows and specifying the extent of the raster, how big or how small you want it. But you also have to mention the CRS or the location information to it. Yes, so let's go on to do a demo. This file is also shared in the RAR folder, RAR file that we shared earlier. If I'm storing this data into temp and using the command raster, let's see how temp looks like. Okay, we see that it's a raster layer. The dimensions are 11 rows, 12 columns, and total number of cells are 132. The resolution is 0.1 and the into 0.1. So resolution in terms of spatial resolution is the maximum distance when we can view two objects separately. So what is the what is the distance of, or what is the dimension of one particular cell? So, and the extent is, if you see here, it is in degree decimal. So probably it is projected in a geographic coordinate system. And here this coordinate system is also defined, latitude, longitude, with the datum as WGS 84. And the value which is available is the temperature value, which is named as BAN, Bangalore Temperature March 2022 file. Okay. Moving on, we can check the resolution of the temp file or the raster data using the command res. So it will show you the resolution of the data set that you have. You can also calculate the summary of the data set that you have. So to understand the summary, what is the minimum, median, max, quantiles, etc., number of NAs, you can use the function called summary and input the raster data here. There is another important function. So if you have a huge data set with a very high resolution, and you want to lower the resolution or make it coarser, you can use the function aggregate. So if we aggregate, it aggregates a raster object to create a new layer with a lower resolution or a coarser resolution. So right now, if I want to reduce the resolution of the temp file by 2. So I use the function aggregate, input the raster file, and then add the factor 2. And then when I check the resolution of the temp AGG file, it is multiplied by 2. Hence, the resolution has become coarser or lower. So there is no right or wrong to what resolution is the perfect. If you want to get into very fine detail, then high resolution works. But like temperature or humidity, which is at a regional scale, you can definitely look at coarser resolution. Now another important function, just like we saw ST transform in vector data. Here it is to transform from one coordinate system to another. We use project raster. Again, you need to specify the raster dataset and the CRS, or the coordinate reference system. Here I have used the, again, universal transverse marketer zone 43. I'm defining it as a string, not as a numeric code. So you can also set the projection coordinate system. So let's do the demo for the if I'm using the project raster function, and you have to define the CRS, and I'm saving it as temp proj. And this string is already defined. I'm not touching it at all. Okay, now let me see how temp proj looks. Okay, so right now the number of cells and columns have changed because it was currently in a geographic, before it was in a geographic coordinate system or as a globe, and now it's plane in meters. So it's in a projected coordinate system. The resolution has also changed. It is not exactly 0.1 degree. It is now 10 kilometer and so on. You can also see that the extent is now in meters, and the coordinate system is in projected coordinate system, not geographic coordinate system. And there are also they have also specified the minimum and the maximum values. Okay, moving on. You can also do some summarizing functions using cell stats. So whatever value is stored in that raster, along with the geographic information, it will calculate the minimum maximum of that value. It can be temperature, precipitation, or pressure, wind speed, or NDVI, or land use, land cover, anything. So you can calculate the cell statistics. You can also do some kind of raster algebra. You can stack 2 or 3 layers one above each other, but you have to remember that they have to be in the same coordinate system. So you can stack one above other and then look at which has the most maximum values, which one has minimum values, or which cell has the minimum value. And you can plot them as well, cell-wise. Since I didn't have multiple layers, so I just took the same file and stored it in 2 different variables and stacked them one over the other using the stack function. And then I plotted the maximum in the stack. So whatever is the maximum in the stack will be plotted here. Now, before we do that, I just want you to check how, when we plot just the temp, how does it look? And when we plot temp projected, how does it look? It looks the same, only the coordinate system has changed. If you just take it 13.5, 72, and for the projected, it is 72,000 something, 720,000 something, etc. Now, suppose if I want to find out, now my vector dataset was the gecko's dataset or lizard dataset. I want to extract the temperature at wherever these lizards are located. So I'm going to use a function from the raster package called extract, where I specify the raster layer first and then the vector layer. And then I run this and I get at each point the temperature. Now I get a useful information out here for the geckos. So all these geckos are found in temperature only at 298, even though the rasters have value of over 300. But still, we got an important information that most of the geckos prefer 298 temperature. Okay, moving on. If you don't want to work with a huge data set and you want to work with a smaller data set or just one gecko's area and look at just that raster layer, we can subset it and then mask all the other values and just focus on that particular region. So for that, I'm going to just use a single rock gamma location using this function. If you see data subset, it's only one rock gamma and the geometry is attached. I'm going to use the st buffer function, which has been used before, and now the specify the distance as 11 kilometers, or should I do it 12? And I just want to look at Let me plot this and plot. If you see, it's a huge circle, the buffer zone, and the point is somewhere in between. Now, I just want to extract the raster data of only this extent of this whole extent, not of the all the area. I can mask the rest of the values and only show the region of interest. How do I do that? Use the command mask, specify the raster, and mask only for this. So only this will be visible. All the rest will be masked. Mask based on this shapefile. Now, if I plot mask raster, then I should just get these. It's probably a circle like this, and only those area has been specified. Moving on, there are multiple raster operations that you can do. You can specify the extent and just see that focus on that, or you can extract different parameters and yes, so on. Now, if you want to calculate the area of a particular raster, so usually what happens, you can first create a raster layer which is of the area. Right now, the raster which we have has the values as temperature. So when we compute this area as area and specify the projected file, it creates a raster layer where each value is the area, not the temperature now. So the if you just view so if you see here, the values were 298 and 300 Kelvin. Right now it has become so and so, which is that now it's an area raster. It's not a temperature raster anymore. And then using the command get values, you get value of each of the value. So there is a 182 number of cells. You get values of all of them and do the sum. So once you do that, you get a particular value and a warning saying this function is useful for is only useful for raster objects with a latitude and longitude coordinates. So you can also use it for a projected coordinate system, and this value is in meter square since our data set is in meter square. So what happens when we don't use a projected coordinate system? We do get the data, but in the degree decimal format, we do get the area. Hence, these are the different ways where you can calculate area. These can be useful when you have a land use land cover data set and you want to calculate value of only the buildings or the urban area. So you can just get values of that raster and do the area calculation. Now that we have looked at a few basic operations in raster package, we'll move on to stars package, which might not make sense a lot right now, but when we start using spatial data, we understand the importance of converting from raster to vector and vector to raster. So this is a beautiful package which in the backend it uses SF as well, and it's still under development. And one of the functions that we'll use today is st rasterize, or convert your SF object to a raster. So let us do that. So this st_raster rasterize is from stars package and not from the SF package. FYI for everybody. So when we do class raster data, it shows us it is from this. The class is now stars class. And when we plot this, now it is no more a discrete data set. It's a continuous data set now. So when we plot data, you see the scale has become continuous, and it's not probably quite visible here, but if you see points here, the black dots on my screen are all rasters. So this is a continuous file with it has moved on from being discrete vector to a continuous layer. And similarly, if you want to convert from a TIFF file to a point file, you know, converting a raster to a vector, then again you can you can read the image or the TIFF file, the temperature file, as using the read stars, not the raster, using the command read stars. So it is now stored as a stars object. The class is star. And then you can use the function which we used in the beginning, converting a foreign object to SF. You can use st underscore as SF, and then you have to mention that we want it as points. So once you do that, you can check the class of SF. So as points is true because we want it as points. And it's now SF object instead of a raster stars object. And when you plot it, it was a continuous data frame, and now it's discrete with values spread all over. So it is now a point and not a polygon raster anymore. Okay, so moving on, we'll just summarize what we did. For the raster package, we were able to read and write. Sorry, I've not shown the example of writing, but it's very similar to what's shown here. Write and add the object which you want to write, and also add the location. You can also adjust the resolution, check the resolution using aggregate and res functions. And then you can do a few geometrical operations like area, mask, extract, and then compute some statistical verbs, some statistics, minimum, mean, and all. And then we also used stars package to do a little bit of conversion from raster to vector and vector to raster. Yeah. Any questions before we move on? Okay, assuming we don't have questions, we'll move on to making maps, the most exciting part. Yes. Right now, we have shared with everybody the Bangalore BBMP boundary, or the municipal boundary, and then I'm just going to name it as Bangalore boundary, and then read the file, add the location, just the shapefile, not the supporting file. So if you see, the projected coordinate system is UTM zone 43. My data set, that is data SF, is in geographic coordinate system, that is latitude, longitude, and not UTM or in meters. So I'm going to convert the Bangalore boundary to the geographic coordinate system. Okay, now my Bangalore boundary is done. Yes, now it's in project, yes, degree decimal and latitude longitude format. Excuse me. I'll also, we'll be using ggplot to plot the static map. So you need to first define the ggplot area, and then I'm going to add two geometric SF. So one is the Bangalore boundary, just like how you do for other objects of point, line, polygon, you specify color, size, alpha, fill. You can do the same thing for geomSF as well. And the other geomSF that I'm adding is our lizard data. That is data. I specify the data as data underscore SF, and the color as blue and size is 2. So it automatically identifies if it's a polygon, point, or line. We don't have to worry about that. So geomSF is very smart that way. And I like things to be simple. So I'm using the simple theme, black and white. You can also add a scale to point out the north and specify the location and the width. Then you can also add a north arrow, and which, if do you want the north to be written there, and any padding X and Y, and also the style. You can keep changing the style as and when required. You can also limit your extent from 77.4 to 77.8, because since it's in geographic coordinate system, I know the values here in easting and northing. So I'm sure all of us have this code, so I'm just going to use it and run it like this. Oh, perfect. So our map is right now made. If you see, there is a north arrow, there is a scale, the boundary, and the alpha, fill, and then the points. So it could identify it's a polygon, and this one is points. And then I also have the coordinate system in easting and northing. So yeah, that is how we make a static map. And now let's move on to something a little more interesting, that is making an interactive map. So usually we use leaflet to make interactive maps. I'm going to add the main data as the Bangalore boundary, and I have to add a base map to this. So I use the add tiles default option, which brings an OSM base map. And then for the polygon that I've added, the Bangalore boundary, I specify the color is green, or any other. If I add even more polygons, it'll all be green. Now, you have to be careful what data set you add here. So I'm adding circles here, and the data as a CSV data set that we read, because here I'm specifying the longitude and the latitude, not the SF object. Only Bangalore boundary is the SF object here. And when I add circles or markers, I'm going to use the CSV data, specify the columns with the same matching the case and the spelling, and specify the radius of the point and the weight and the fill. So once you do that, I'm going to run this. Perfect. So you have this map. You can reduce the width of this size of this circle, and then you can pan, zoom into this, or change the color, and go into each location and see where did you find this agama or the lizard? Was it inside the near water body or no? So that completes our demo. So there are a lot of different data sources for working with spatial data. There is Natural Earth, there is OpenStreetMap, which provides open source road data, railway data, and canal data as well. There is free elevation data set available. If you're interested in wildlife, there is MoveBank, which gives animal movement data. And there is also GHSL, which provides population data, and USGS island data. If you want to learn more about spatial data, SP data is a very good data set which has diverse spatial data sets for understanding and teaching spatial analysis. But sometimes making maps in R is not easy. So it's sometimes slow, and the transformations can be a little difficult, and adding annotation can be very tedious. So that's why people prefer to move to QGIS or ArcGIS to do such things. These are the resources that we have used. Thank you so much. We'll move on to a 20-minute exercise. The file will be shared now, and then we'll take the questions. Thank you so much.